Good morning, Hassler here. We're going to take some notes for section 2.7 on limits at infinity. And what that really means is we're going to be looking at the end behavior for particular functions. We're going to start out with the easy functions, and then in part 2, I'll discuss what happens with the rational functions. Okay, so it says sketch a graph of each function and determine the limits at infinity, the end behavior. All right, so if I have the function y equals 7, well, that's a constant function. In other words, that's just a horizontal line at the y value of 7. And when I look at the end behavior, what I'm talking about is what's happening as my arrow continues moving further and further to the right. That would be the limit as x approaches infinity, right? So when we look at end behavior, we're looking at my x values getting larger and larger and larger for this particular function. And I didn't call it f of x, I just called it y. You can actually write the function in there. So I'll say the limit as x approaches infinity for my function is equal to 7. Well, in this particular case, a constant function, the y values are always going to be 7. It doesn't matter where the x is, okay? But if we're looking at end behavior, we have to look at what's happening on the left side as well. And so I'm going to say the limit as x approaches negative infinity for my particular function. And again, because this is a constant function, the y values will always be 7. And so instead of saying that we're approaching a specific x value from the left or the right side, or overall, we're going to be looking at limits as the x values grow exponentially larger in the positive direction, or larger and larger and larger in the negative direction. In other words, we're looking at limits as x approaches infinity or as x approaches negative infinity. All right, 2, y equals 2x squared. If I were to graph y equals 2x squared, I would have a parabola with a little bit of a vertical stretch, okay? And again, I'm looking at the end behavior. What's happening to my function as my x values continue to grow more and more positive? Well, the limit as x approaches infinity for this particular function, I know it's hard to see that the x values are growing larger and larger and larger because it just looks like the function is moving upwards. But as the function is moving upwards, my x values are also headed out to the right. I'm putting larger and larger x values into the function to get larger and larger y values. So as x approaches infinity for this function, 2x squared, my y values will also be approaching infinity. My y values will also be growing larger and larger and larger. And I need to see what's happening on the left side, or the limit as x approaches negative infinity of this particular function. And again, my y values are also headed towards infinity. So as I continue to put x values that are more and more negative into my function, my outputs are going to continue to be more and more positive. I'm squaring those negative numbers. All right, last example for the basic functions. I have y equals 1/2 x cubed. So x cubed looks something like this, and the 1/2 is going to vertically compress that. So again, we're looking at the end behavior, and I should have done that in red. My apologies. So the end behavior on the right side, again, the right side end behavior means we're looking at the limit as x approaches positive infinity for my function, and that is going to be equal to infinity. As my x values grow larger and larger, my y values grow larger and larger. And I want to look at the left-sided end behavior. In other words, I want to see what happens as x approaches negative infinity. So the limit as x approaches negative infinity for my function, well, my y values are also approaching negative infinity as I continue to move downward in the negative direction. So again, when we talk about end behavior of a function, end behavior of a function means I'm looking at the limit as x approaches positive or negative infinity, okay? So when we're talking about end behavior, we're looking at the limit as x approaches positive or negative infinity. So just a quick reminder from Algebra 2 trig and then from pre-calc. In general, if y is equal to x to the n, and what we're talking about here when we say y equals x to the n, we're talking about polynomial functions. Okay? Things like what we did up above, constant functions, quadratic functions, cubic functions, lines, etc. For all natural numbers n, that means the exponent is 1, 2, 3, 4, 5, 6, 7, etc. The limit at infinity is as follows. So if the exponent, n is the exponent, if the exponent is even, okay, so in other words, if I have y equals ax to the n, and the exponent, this n, is even, I'm going to have two scenarios occur, okay? I'm either going to have a positive a value, which means I'm going to have a graph where my two ends are going to be moving in the upward direction. So this would be an x squared graph, x to the fourth, x to the sixth, etc. Okay? And when I have a graph like this, the limit as x approaches infinity for that function is infinity, headed towards positive infinity. And the limit as x approaches negative infinity for this function is equal to also infinity. Okay? So when I have a positive leading coefficient, that a value is positive, and I have an even exponent, I would have a graph that looks like this, and my end behavior would be written as the red and the blue limits. But there is another scenario. So that other scenario occurs when that a value is negative. Okay, so if I have a negative leading coefficient, then the graph that I get when my exponent is even is facing downwards. So this would be like a negative x squared, negative x to the fourth. And as you can see, that's going to change our limits. So the limit as x approaches infinity of this particular function would be negative infinity. And on the left side, that left end behavior, the limit as x approaches negative infinity of my function is also equal to negative infinity. So this is something to recall from, like I said, Algebra 2 trig or pre-calc or the honors versions of those, okay? Okay, so what happens if n is odd? All right, so again, if I have y equals ax to the n, and this time the exponent is odd, n is odd, and I'm going to start with a positive leading coefficient. The graph of this would look something along these lines. This is like the third example up above where I would have x cubed, x to the fifth, x to the seventh, where my end behaviors are going in opposite directions. And as we said up above, the limit as x approaches positive infinity for this function is equal to infinity. That's the right sided behavior, okay, end behavior. And then the limit as x approaches negative infinity for this function is equal to negative infinity, because this time my end behavior on the left side is moving downwards. Okay? And again, that happens when the a value is positive. So let's take a look at an example when the a value is negative. So again, I still have an odd exponent, okay? And my a value this time is negative, which means I'm going to reflect over the x-axis. So I end up getting a graph that looks like this. So negative x cubed, negative x to the fifth, etc. So the limit as x approaches infinity, that's that right-sided end behavior for my function, is equal to negative infinity. And the limit as x approaches negative infinity, the left-sided end behavior of my function, this time is positive infinity. So things to keep in mind as we go through the next section is what would the end behavior look like for a given polynomial function. And then we're going to use that to apply whether or not a rational function has an overall limit, or if the overall limit technically does not exist. Remember, anytime my overall limit is headed towards infinity or negative infinity, technically overall that limit does not exist. All right, I'm going to get ready for part 2.